a short video to remind you of hybridization. So the three hybridization states, the sp3, sp2, and sp. So we were talking about alkanes, and we said that alkanes, and the simplest alkane here we're going to talk about is methane. All carbon-hydrogen bonds are equivalent. All are directed toward the corner of a regular tetrahedron with the carbon at the center. And the bond angle here, hydrogen, carbon, hydrogen, is around 109 and 28 degrees. If all carbon-hydrogen bonds are equivalent, they have the same length, and they are all away from each other with the same angle, that means they come from exactly the same type of orbitals interaction. Let's look at hydrogen and carbon. So hydrogen has only one electron, and this electron is in 1s orbital. So there is only one electron in 1s orbital. The carbon has 6 electrons in total. So there are 2 electrons in 1s orbital, 2 electrons in 2s, and 2 electrons in 2p. And we know that the p orbital is formed of 3 suborbitals, 2px, 2py, and 2pz. So in the normal, without hybridization, the normal electron distribution of carbon, the s orbital will have 2 electrons, and the px and py will each have 1 electron, and bz doesn't have any electrons. If you look at this, then you would think that for the carbon to make 4 electrons, it's impossible, because it will form only 2 bonds with the 2 unpaired electron in the px and by, while we have a pz as an empty orbital. So what happens is there's what's called hybridization. So hybridization here takes place between all the 3p orbital and the 2s orbital to make a mix of 4 new molecular hybridized orbital, and all of these will be equivalent to each other. So we know that the 2s has lower energy than the 2p. Now, when we mix all these orbitals, we will end up with 4 similar orbitals with similar energy. The energy here will be between the energy of the 2s and the energy of the 2p. So the 4 orbitals will be formed, they will be called sp3. Why sp3? Because it's formed of 1s and 3p orbitals. The hybridization, or the mixing of all the 4 new orbitals, will give you a new set of 4 similar orbitals, and they will be arranged they will have a tetrahedral arrangement. And this tetrahedral arrangement will give the very common shape, or well-known shape of the sp3 hybridized carbon in alkanes, which are the tetrahedral one. Now you have a central carbon with 4 hybridized orbitals, 4 valence orbitals. Each is sp3 hybridized orbital, and you have the hydrogen with 1 s orbital. The sigma bond will form by end-to-end combination between or interaction between the between the sp3 orbital of the carbon and the s orbital of the hydrogen. This will result in the sigma bond, which is the characteristic type of bonds we only find in alkane. So there is no other bonds of alkane. It's all sigma bonds. All bonds are sigma bonds, and all bonds are equivalent. They have the same length, they have the same strength, because they result from the combination or interaction between an sp3 hybridized orbital of the carbon and 1s orbital of the of hydrogen. If we move on to the other alkanes where there is a carbon and carbon, the sigma bond here will be between sp3 hybridized orbital of one carbon and the sp3 hybridized orbital of the second or of the other carbon. Another example of sp3 hybridization will be found in ammonia. NH3. So here the hydrogen again has only one electron in one s orbital. The nitrogen in total has 7 electrons, so 2 in one s, 2 in 2s, and 5 and 3 then in p orbitals, 1 in each of the suborbitals of the p orbital. Now the mixing again will take place between the s and the 3p orbitals, but we will end up with one orbital with 2 electrons, paired electron, and the 3 others will have only one electron. This is why in ammonia and NH3 you always have a lone pair of electrons. This lone pair of electrons doesn't take place in interaction, it doesn't form bonds, but only the 3 sp3, the other remaining sp3 hybridized orbitals which have one electron will form bonds. Again, it will have the same tetrahedral arrangement, but this will include the lone pair as well. Now look at water. The oxygen has 8 electrons, so in total, when the sp3 hybridization takes place, it will have 2 sp3 hybridized orbital each with a lone pair of electron. The characteristic 2 lone pair of electrons you can find in an oxygen, and 2 single or unpaired electrons in the other sp3 hybridized orbital, which will form the 2 bonds you usually find with the oxygen. So what about the sp2 hybridization that we will find in ethane and alkenes? So in case of alkenes, so the carbon again will have the same distribution of electrons like the carbon before. But now instead of the mixing between the 3p orbitals and the s orbital, the mixing here will take place between one s orbital and 2 of the p orbitals, leaving the third one as it is as a p orbital. So this is why it's called sp2. Again, the electrons will distribute themselves in a way that all the p orbitals will have one electron, and the other, not the p orbital, all the orbitals will have one electron. One of them will remain as a p orbital, and the other 3 will form the sp2 orbitals. The sp2 orbital again will be a mix of one s and 2 of the p suborbitals. The sp2 hybridized orbitals will give a different arrangement in space. It will give a trigonal planar arrangement. This is why alkenes are planar, while alkanes are non-planar. So now we're going to have a trigonal planar arrangement of the orbital in comparison to the sp3 orbitals. Ethane is a flat molecule that has 2 equivalent carbons and 2 hydrogen, and all the 6 atoms in ethane are in one plane. So the trigonal planar arrangement of the 3 hybridized orbital of ethane will give it the characteristic shape. The bonding of ethane results from the same orbitals, 1 2s and 3 2p, but with a difference that one of the 2p orbitals will not participate in the hybridization. So you will have 3 sp2 orbitals that will form sigma bonds. One of these sigma bond will be between 2 sp2 orbitals, between the 2 carbons, and the other 2 will be between an sp2 orbital from carbon and 2 and 1 s orbital from the hydrogen. The other p orbital that will remain will form the double bond in the ethane. The remaining p orbital on both of the carbons of ethane will now overlap with each other to form the other type of covalent bonding, which is called the pi bond. The overlap here will be side to side, in contrast to the end-on overlap that takes place between the sp3 orbitals or sp2 orbitals with the s orbital altogether. So the hybridized orbitals will overlap with other orbitals in an end-to-end to form the sigma bond, but the 2 pi bonds, the 2 p orbitals from the 2 carbons will overlap side to side to give you the pi bond. Because sp2 orbitals form between one s orbital and two p orbitals, so it will has more s character. That means it's going to be a shorter bond. It's closer to the nucleus. So the bond here is going to be shorter. There's also a change in the angle now. The angle between the bonds will be 120. It's a trigonal planar. This is the best way to keep all the bonds as much away from each other in space. It's a planar one, and the maximum angle you can get between three equivalent bonds around a point is 120. The pi bond is formed between a side-to-side overlap between two pi b orbitals, and in this case, the pi bond is much weaker than the sigma bond. So this side-to-side interaction or this side-to-side overlap will generate a pi bond which is weaker than the sigma bond. This is why ethenes or alkenes are much more reactive than the alkanes. The last type of hybridization is sp hybridization, and you will find that in alkynes. So ethine, which is the simplest alkyne, of course, because for alkynes you need to have a minimum of 2 carbons to form the triple bond. The type of hybridization now is an sp. Again, it's the same arrangement, but now the combination will take place between one p orbital and one s orbital, and two p orbital will remain as they are. And in the same way, we talked about the sp orbitals, sp2 orbitals. The sp orbital will form a sigma bond with the s orbital of the hydrogen or with another sp orbital from the other carbon to give you end-to-end overlap to give you the sigma bond, while the other two orbitals will have side-to-side overlap to give you two pi bonds now.